Over the past several videos, we've been looking at the mechanics of matrix multiplication. In this video, I want to give some geometric meaning for why matrix multiplication is defined the way it is. Let's jump right into it. To better understand the context for when we might multiply two matrices together, we need to define the notion of a linear transformation. So a linear transformation is a function from Rn to Rm so that two properties hold. The first tells us basically that scalars pull out. So t of kx is k times t of x, where k is a real number and x is a vector in Rn. The second tells us that the transformation of a sum is the sum of the transformations. T of x plus y equals t of x plus t of y, where here x and y are any two vectors from the domain Rn. Before I go into a global classification of every possible linear transformation, let's focus on the functions which are most familiar to us. So let n and m both be 1 so that we're looking at functions from R to R. In other words, functions of the form y equals f of x. Take a moment to take a few functions from R to R and check if they are linear transformations. What you may have realized is that any scalar valued function of a single variable, which is a linear transformation, must have the form t of x equals m times x. So for example, t of x equals 2x or t of x equals negative 3x. If you checked quadratic functions or any other kind of function, you would have found that it wasn't a linear transformation. So linear transformations from R to R have a very prescriptive form. Over the next several minutes, I will generalize this prescriptive form for linear transformations from Rn to Rm, but before we do that, let me give you a shorthand way to test these two properties. The two properties that we require for linear transformation, the idea that scalars pull out and the transformation of a sum is the sum of a transformation, these two properties hold if and only if the function t sends the linear combination ax plus by to the linear combination a times t of x plus b times t of y. So here a and b are scalars and x and y are vectors. So I like to think of it as linear transformations preserve linear combinations. They send a linear combination to an analogous linear combination. If you'd like, you can take a moment here to pause and see why this single test can replace the two at the top. It really just amounts to choosing the correct values of a and b so that the possible linear combinations that we consider include a single act of scalar multiplication as well as basic addition. What I would like to do now is think about the properties of matrix multiplication and compare the properties we know about matrix multiplication to this new test. So in particular, consider any m by n matrix capital A, and imagine that we have two scalars, little a and b from the set of real numbers, together with vectors x and y from Rn. If I form the linear combination ax plus by, and then act on that from the left with the matrix A, what happens? We know that matrix multiplication is distributive, so the first thing I can do is distribute A to the scaled vectors little ax and by. But then we also know that scalars can pull out in front, so I can think of this as little a times the matrix product ax plus little b times the matrix product ay. Just a quick dimension check here. Notice a is m by n. Since x and y are from Rn, so is any linear combination of them. So what we are acting on with the matrix A is an n by 1 vector overall, which means the result on the right-hand side will be m by 1. So this act of matrix multiplication with the matrix A sends us from vectors in Rn to vectors in Rm, and therefore what we recognize is a type of linear transformation. So if we define a linear transformation by t of x equals ax, here the matrix A is fixed, and we're saying to transform x, multiply x from the left by the matrix A. This creates a linear transformation from Rn to Rm. The question is there any other type of linear transformation? So let's think more generally. Suppose that I have a linear transformation t from Rn to Rm, but I don't yet have a prescriptive form for it. Can we actually figure out what t must look like? Imagine we have any input x from the domain Rn. Since x is a vector, we can break it down into its first coordinate times the first standard basis vector, plus its second coordinate times the second standard basis vector, all the way through its nth coordinate times the nth standard basis vector in the usual way. We've done this before, which means if I want to say t of x, I can now write that as t acting on this decomposition for the vector x. But t is a linear transformation, so in particular, I can break it up across all of this addition, and I can pull all of those scalars out. Here, the scalars are the coordinates of x. What we have now on this third line is a linear combination of the vectors t of e1, t of e2 through t of en. Sometimes it's harder to go in this direction, but if you remember, when we talked about matrix multiplication through the lens of looking at the columns, what we discovered was that any linear combination of vectors can be represented as a matrix times a vector. So from this linear combination, I can write this matrix product, where the columns of the matrix are the vectors t of e1 through t of en, and the weights x1, x2 through xn that form the linear combination become the entries in a vector. Let's give these two objects a name. The vector we already know is x. That's actually what we started with. And then let's call the matrix A. Look at A. It has no dependence on the vector x. It is only determined by how the transformation acts on the fixed standard basis vectors of Rn. If I had taken a different starting vector x, we would have the exact same decomposition with the exact same matrix. So it's fair to say that this linear transformation can now be thought of as the matrix A times x, where A is a fixed, determined matrix. All you need to know to get A is how T transforms the standard basis vectors. Okay, so to summarize, what we've discovered is that any matrix gives you a linear transformation via multiplication with that matrix. But now we can also say that if you know you have a linear transformation, then that means that there is some matrix out there, so that your linear transformation must take the form t of x equals a times x. The conclusion is that linear transformations and matrices go hand in hand. So T is a linear transformation from Rn to Rm if and only if there exists an m by n matrix A, so that you can say T of x equals A times x. That's how T acts on any vectors x from the domain Rn. I've given you here some terminology that you can use to describe this association. It's important to recognize that while matrices define linear transformations and linear transformations have associated matrices, the words linear transformation and matrix are not exactly synonyms. So a linear transformation is a kind of function, whereas a matrix is just a rectangular array of numbers. So they're not the same, but they are closely linked. For linear transformation, you can say that you have an associated matrix A, or you have a matrix representation. A defines the action of a linear transformation. So just be careful that when you look at a matrix, you don't call it a linear transformation. Rather, you recognize that it describes the action of a linear transformation. Okay, getting a little bit pedantic, so let's move on. In particular, I want to return to our study of matrix multiplication. Suppose that we have two matrices A and B. A is an m by n matrix and B is an n by p matrix, so we know we can do the matrix product A times B since their inner dimensions match. We also know from the discussion that we just had that 2A we can associate the action of a linear transformation from Rn to Rm, I'll name it T sub A, and likewise 2B we can associate a linear transformation T sub B, mapping us from Rp to Rn. Take a moment there just to recognize how the dimensions of the matrix relate to the dimensions of the domain and what you could call the codomain. So you want to develop the instinct to kind of flip them. Okay, so let's take a vector C from the domain Rp for the second linear transformation. Since the codomain for T sub B is Rn, and that's the domain for T sub A, we can do this composition. Basically, this composition is well defined. So we can say what's T of A of T of B of C. Working from the inside out, we can say TB of C is just matrix multiplication B times C. That forms a vector in Rn, and TA of that vector, again, is just the action of matrix multiplication with the matrix A. So now we have A times B times C, but matrix multiplication is associative. So we can say that M by P matrix AB is associated with this composition, this function that we formed by composing TA and TB. And since that composition has an associated matrix, that tells us actually that the composition of linear transformations is a linear transformation in its own right. That wasn't immediately obvious until you check it. So actually what we've reached here is a really important fact about matrix multiplication. When you first learn matrix multiplication, perhaps as a child, it seems extremely strange. Why do we do this dot product style operation with the rows of the matrix on the left and the columns of the matrix on the right? Why don't we just do entry by entry products like when we learn addition? And the reason matrix multiplication is defined the way it is because it agrees with the action of composing linear transformations. So matrix multiplication isn't just an algebraic algorithm, it has a geometric meaning. And with that understanding, we can actually form new matrices out of building block matrices, which we've actually already met in a previous video. Let's work through a total of 4 examples, starting with these 2. I would like to find the matrix which reflects R2 over the x-axis and then rotates the result by some angle theta. Just a little note here, if I say plane rotation without further precision, I mean in the traditional counterclockwise direction. So in this example, we are going to apply multiple linear transformations one after the other. The first linear transformation that we want to consider is the act of reflecting the xy plane over the x-axis. In an earlier video, we were able to write down the explicit matrix that would perform this action by thinking about how it would have to act on the standard basis vectors. It fixes E1, but it flips E2, so that the matrix which reflects R2 over the x-axis is 1, 0, 0, negative 1. Okay, so the linear transformation we're looking for will do that first, and then it will rotate the result counterclockwise by some angle theta. We also thought about how rotation affects the standard basis vectors to form this matrix. So we've seen these 2 matrices already. Now we would like to apply one and then the other. So we have to do the matrix product of the second matrix on the left with the first matrix on the right. Be careful there with the ordering. The result is this 2 by 2 matrix. Cosine theta, sine theta, sine theta, negative cosine theta. So composing these 2 actions one after the other can be described as a matrix product. Again, be careful here with the ordering. If you didn't understand why I wrote the second matrix before the first one, think about how this product would act on a vector. The one on the right hits the vector first, and then the one on the left. So that's why the ordering here goes right to left instead of left to right. Now let's work through the second example. You may enjoy pausing and writing down the result first. I'll go through it in just a moment. Again, we have the composition of 2 linear transformations. This time we want to rotate first and then reflect. It's the same matrices as we just saw. This time the rotation matrix happens first and then the reflection. Same matrices, reverse the order, and we get this 2 by 2 matrix. Cosine theta, negative sine theta, negative sine theta, negative cosine theta. Notice it's not the same matrix as we had in example 1 because matrix multiplication, as we know, it's famously not commutative. And now you can associate some geometric reason why it's good that it's not commutative, because reversing the action of linear transformations is not necessarily commutative. I don't have an illustration of this for examples 1 and 2, but you can draw a picture on paper. Take a vector, reflect it over the x-axis, and then rotate it, and then do vice versa. As long as your angle of rotation is not 0 or 180 degrees, you will get a different vector. Okay, let's move on to example 3. I really enjoy these exercises. What we are going to do is create the matrix which will project the xy plane onto the line y equals mx, where the slope m here is just some real number. Let me remind you of how projection works. If I want to project the xy plane onto this pink line, the line y equals mx, it will fix the line, and it will basically collapse the rest of the plane onto this line in a perpendicular fashion. So if you imagine some vector which is not pointing along the line, and you drop an altitude or a perpendicular component from the head of the vector straight down to the line as I've illustrated here, then the projection of this vector onto the line is that darker vector I've sketched, which gives us what I often think of as the shadow of this vector on the line. More precisely, what we form here is a right triangle where the original vector is the hypotenuse, and then one of the legs of the right triangle lives on the line, the other is perpendicular. We are looking for the vector representation that I've sketched here, which lives on the line. You might not yet know that this is actually a linear transformation, that it would satisfy the definition of a linear transformation, but I'm going to create a 2 by 2 matrix that will return us this active projection. And since I can describe it with the 2 by 2 matrix, we will know that projection onto this line is indeed a linear transformation. To come up with this 2 by 2 matrix, I'm going to do a 3-step process. The first thing I'm going to do is imagine rotating the xy plane clockwise so that the pink line gets sent to the x-axis. So in this picture, that looks like about a 40-degree clockwise rotation. If you're looking at this image, what you can do is tilt your head a little bit to the left so that the pink line seems like the flat ground. Projecting onto that line is then like projecting onto the x-axis, so it would be straight downwards projection. So then after the act of projection has happened, we will rotate counterclockwise to put the pink line back where it started. So the principle is rotate the pink line so that I like it better. I would like it better if it was the x-axis because I can project down onto the x-axis and then rotate to put it back. Each of these actions is a matrix which we can immediately write down. So we have rotation. We will rotate clockwise by this angle theta. Quick remark about that angle. Notice that the point 1m lives on the line. You can compute the angle theta that the line opens with the positive x-axis by doing arctan of a known y-coordinate divided by a known x-coordinate. So explicitly, theta here is arctan of m. Okay, just put that aside though. The rotation matrix that will send the pink line to the x-axis is rotation by negative theta. Traditional rotation is counterclockwise, but negating theta here will move us in the clockwise sense. Cosine is an even function, sine is an odd function, so it's often nicer to write this clockwise rotation as the matrix whose first column is cosine theta negative sine theta and whose second column is sine theta cosine theta. Take a moment to recognize here how cosine being an even function and sine being an odd function allowed me to handle the negative inside the argument. That is the first linear transformation that we will perform on R2. Then we want to project onto the x-axis. Again, that's a matrix which we can easily write down by thinking about how projection affects the standard basis vectors. So that 2x2 matrix is 1, 0, 0, 0. Now we just need to move the line back to where it started. That is again rotation. This time it's traditional counterclockwise rotation. So here's the famous 2x2 rotation matrix by angle theta. These matrices are associated to 3 successive linear transformations that we need to compose. So the appropriate matrix product goes right to left like this. And then if we multiply them together, we get this 2x2 matrix in terms of cosines and sines. And if you want to write it a little bit differently, you can write this 2x2 matrix, where I've used the fact that theta here is arctan of m. Notice if m is 0, then this reduces down to just projection onto the x-axis. If we let m go to infinity in the second line, you can actually do that. You end up with 0, 0, 0, 1 in the bottom right corner. Or you could say that would be like having theta equal pi over 2 in the first representation. Okay, so here's how we came up with a nice 2x2 matrix representing the idea of projecting the xy plane onto a line by thinking about that action as the composition of known linear transformations with matrices that we've already worked out. And because matrix multiplication encodes the action of composition of linear transformations, we can do this triple product to solve example 3. We'll wrap up with this example. It's very similar, so I encourage you to pause and work through this on your own. I'll put up the answer a little bit more quickly in just a moment, but what we would like to do is find the matrix which reflects the xy plane over the line y equals mx. Okay, let's see if your matrix is the same as mine. It's the same 3-step process, it's just the middle action will be a little different. So our first step is to rotate the xy plane in such a way that that pink line gets sent to the x-axis. So what I've put here is the same rotation matrix as before. Then we want to reflect over the x-axis. We've seen that before, but if you don't remember it, it's not hard to come up with this 2x2 matrix by thinking about how that action moves the standard basis vectors. And then we want to rotate back. That again is our traditional rotation matrix. With the correct ordering here, where the final transformation is the first one in the product, we get this 2x2 matrix. Here, I think it's nicer to leave it in this form with sines and cosines. Okay, that wraps up this lesson. There were 2 main take-home messages. The first is that to any m by n matrix, we can associate the action of a linear transformation from Rn to Rm. And then the second take-home message, tying back to our lessons on matrix multiplication, is that when you multiply 2 matrices together, what you are actually computing is the linear transformation you would get by successively applying their associated linear transformations. Okay, thank you for your attention.